Hello everyone, let's take a look at this projectile motion problem from the OpenStax textbook. A football player punts the ball at a 45-degree angle without any effect from the wind. The ball would travel 60 meters horizontally. So that's our setup. And there are two parts to this question. I'd recommend just focusing on the first part. We'll get to part B later on. So for part A, what is the initial speed of the ball is the question. Always good to draw a picture of what's going on. So maybe you want to draw the ground and have the ball somewhere there. And you might say, okay, the ball has an initial velocity at a certain angle. They give you the angle, 45 degrees. So I'm writing this down and marking V naught, and then it's a vector, right? So that's the initial velocity. Just kind of sketching a diagram of what this might look like. It doesn't have to be too artistic. It just needs to capture the basics of the problem. Now, this is what's happening, and you can imagine how the ball might travel once the person punts the ball. The ball might kind of go like that, right? And follows this path, more or less, right? Just roughly, what path would it take? You can also watch a video of someone doing this, right? So on YouTube, you can see somebody punt the ball and see how this ball would move. So kind of a rough idea of how the ball would go through space like this. And once we have this, what you want to do is think about a coordinate system to use. The one I'm going to use is centered at the starting point of the ball, right? So if we start where the ball starts, put our x, y coordinate system at that point, we can measure distances from that point onward, right? So when the problem says it travels 60 meters, it means from the starting point, it traveled that far, right? So 60 meters. What we're asked to find in the first part is the speed, right? So how fast did the person punting punt the ball? What's the speed? So velocity is a vector, but we're really after the magnitude, right? That's what we're after here. What's the magnitude of the velocity? Okay, so that's the setup of the problem. This is kind of what's going on. Now we'll have to think about, so how do we solve this problem? What we want to do is think about our kinematic equations. This motion is in two dimensions, x and y. So let's write down our kinematic equations in both dimensions. So we'll start with the y, right? So the final y is equal to the initial y position plus the initial velocity in the y direction times time plus 1/2 at squared. Okay, so one of our kinematic equations. And we can also do the same thing with the x, right? So the x final position is equal to the x initial position plus the initial velocity in the x direction times time plus 1/2 at squared. And so we can specify the accelerations in the y direction, the accelerations in the x direction, right? So they're symmetric, exact same equation, just writing it for x and y. In the case of x, what we're going to say is we're going to get rid of that acceleration term because we're ignoring the effect of the wind. We'll get to the wind in the second part of the problem, but for the first part, we're just completely ignoring the wind just to get an idea of how this would work if there was no air resistance. In that case, there's no acceleration in the x direction. Okay, there is certainly an acceleration in the y direction. That's the acceleration due to gravity, right? So downward is an acceleration that's negative 9.8 meters per second squared. All right, so that's there. We have to account for that. Now, notice when we're trying to solve this, there's something common between the two equations, and that is the time, right? That is common between the two. The time we're talking about in the y equation is the same time we're talking about in the x equation, right? Just something to notice. Don't forget, our objective is to find the initial speed, right? So using these two equations, we're going to try to solve for that initial speed. Okay. So let's try to simplify these equations a little bit. There's a lot of terms. Some of these are zero, right? Can be set to zero. Let's start with the y. Y, the final position in y and the initial position in y, right? Both could be set to zero, right? Because this ball is going to start from the 0, 0 point, and then when it ends up later 60 meters away, its y value is still 0, right? So before and after, the y value will be both 0, right? So that simplifies this equation. On the x side, x naught could be set to 0 because the starting x position is 0, right? Okay, so then what does that leave us here? The y equation is 0 is equal to v naught y times t plus 1/2 a t squared. And I'm just going to write a because there's only one a, right? So it's a y, but we don't need to write that. X is equal to v naught x times t. That's all that's left on that equation, right? So we're starting off with a velocity that's 45 degrees, right, off the ground. It has components, right? That's why we have these subscripts. The initial velocity has a component in the y, and it has a component in the x, right? So let's think about that a little bit more. Sometimes the trouble is to break up vectors into component parts. So we want to become familiar with going through that process, right? So here, I'm just redrawing that velocity vector that we had before, v naught, right? The magnitude of that vector, just copying that over from our diagram. And now I want to come up with the components of this vector v naught. And when I'm breaking up a vector into component parts, what I'm trying to do is make a right triangle, and the two sides, the other two sides, besides this hypotenuse of the right triangle, follow the same direction as the y and the x, right? So if I want to create a right triangle, I'm going to start at one end of the vector and just draw downward along the y axis. And same thing with the x, right? So starting at the other end of the vector, I'm just drawing a line that goes along the x direction, right? So now I have myself a right triangle, and the part of the velocity that's in the y direction, v naught y, is like that, and then v naught x is like that, right? And then we know that this angle is 45 degrees. So now you can use a little trig to figure out what these parts are using a little SOHCAHTOA, right? So remind ourselves our mnemonic, SOHCAHTOA, right? So all reference to the angle 45 degrees, right? So when I write sine of 45 degrees, right? What's its opposite? Well, 45 degrees, the opposite is v naught y, and its hypotenuse is v naught. So this allows us to solve for v naught y is equal to v naught sine of 45 degrees, right? So that's what we need, and we need these components to solve our kinematic equations, right? V naught y appears in our y equation here, right? So we need to come up with those components. let's do the x part, right? So if we do cosine of 45 degrees, then what's the adjacent to that angle? Well, that's v naught x. What's its hypotenuse? Again, v naught. This allows us to solve for v naught x is equal to v naught cosine of 45 degrees, right? So now we have these components. We can go and plug them into our kinematic equations at the top here, right? When we need v naught x, we have it. When we need v naught y, we have it. Now we can go ahead and plug them back in. So we have 0 is equal to, right? Putting v naught y in here, we have v naught sine of 45 degrees times t, right? And just replaced v naught y with what we came up with our trig, plus 1/2 at squared, right? That's our y equation from the top. Now let's do that with our x. X is equal to v naught cosine of 45 degrees times time. Okay, so now we have put in those trig the results of those trig identities. We have now put them in. So now the x equation we can solve for time. Time is equal to x divided by v naught cosine of 45 degrees. Right, just solving for time. As I said before, the time is the same for both equations, right? What we mean by time is the same. So now once you solve for time, what you can do is substitute time into the y equation, right? So it's going to get a little messy, but we can be careful and keep track of all our terms, hopefully not lose anything along the way. So we have 0 is equal to v naught sine of 45 degrees, right? That's just as before. Now we substitute for t, x divided by v naught cosine of 45 degrees, and add that to 1/2 a. Still have to substitute for t, but don't forget the square. So x divided by v naught cosine of 45 degrees, and then squared, right? So the y equation is now a little more complicated, but we'll slowly try to simplify it so that we can solve this. Okay, so a couple of things will cancel, right? So v naught here will cancel, and yeah, so let's leave that and then try to rewrite this. So if 0 is equal to x, sine divided by cosine is tangent, trig identity, right? So sine divided by cosine is tangent 45 degrees, plus 1/2 a. We have a x squared divided by v naught squared cosine squared of the 45 degrees. Okay, now what we wanted to do to simplify a little bit is we can divide all the terms, both sides, by x. If you divide by x, you have 0 is equal to tangent of 45 degrees plus ax divided by 2 v naught squared cosine squared of 45 degrees. Okay, so getting better, but I still have to clean this up a little bit. What we'll do is move the tangent to the left-hand side, so we have a negative tangent of 45 degrees is equal to ax divided by 2v naught squared cosine squared 45 degrees. Okay, and I'm going to switch terms. We're going to switch the v naught. We're trying to solve for v naught, right? So that's our objective. So let's move and isolate that. So we have v naught squared, right? Multiplying both sides by v naught squared leads us v naught square on the left-hand side, and then I'm going to divide everything by negative tangent of 45 degrees, right? So doing a little bit of algebra, moving the terms around here, and that will leave me a x divided by minus 2 tangent of 45 degrees cosine squared of 45 degrees, right? Now, when I see that, I know tangent is sine divided by cosine. So just to simplify, what I'm going to do is just put sines and cosines back there, right? So I'm going to say this is equal to ax divided by minus 2 sine of 45 degrees divided by cosine of 45 degrees, right? Just rewriting the tangent. And then I have a cosine squared of 45 degrees. All I'm trying to do is clean this up and get it to the simplest form as I can. So now one of the cosines will cancel, the one at the bottom and the one that's squared, they can cancel each other. This leaves you with v naught squared is equal to ax divided by minus 2 sine of 45 degrees cosine of 45 degrees, right? So one of the cosines here cancels with one of the ones here because that's just two cosines multiplied together, right? So now we just have sine and cosine, right? So now to get the velocity, v naught, all you have to do is take a square root. So square root of all of this, ax divided by minus 2 sine of 45 degrees cosine of 45 degrees. And you can put this on your calculator now. We've gotten to the simplest kind of form on algebraically. So now you can go ahead and put this into your calculator. For A, the acceleration due to gravity is negative 9.8 meters per second squared. We're sticking to our convention, right? So acceleration is negative because of our coordinate system with up being positive. So you have to follow that. Once you establish a coordinate system, you have to stick to it throughout the problem and be consistent. Otherwise, you'll get an incorrect result, right? So negative 9.8 meters per second squared times x. And the x we're using here, going back to remind ourselves, when we mean by x, it's the final position of the ball in reference to the initial position. So that final position is 60 meters, right? So when we mean by x, we mean the 60 meters. So 60 meters goes in there, divided by negative 2 sine of 45 degrees, and then times cosine of 45 degrees. Putting all this into your calculator, you'll get 24.2487. I'm not going to do the proper significant figures here because I want to carry all the decimal places for the next part of the problem. But if you're going to give this as an answer, just be careful about putting the right number of significant figures in here. You don't want to just list a lot of decimal places. But for the purposes of carrying this forward, we're going to need this number in the next part of this problem. So it's good to have more decimal places for accuracy purposes. Okay, so now that's the first part of the problem. We've figured out how fast this person punted this ball. Okay, so let's think about the second part of this problem. When the ball is near its maximum height, it experiences a brief gust of wind that reduces its horizontal velocity by 1.50 meters per second. What distance does the ball travel horizontally, right? So right off the start, you should think about, do you expect the ball to go further down or kind of a shorter distance, or the same, right? So before, when we considered the person punts the ball, it travels. We don't account for any wind affecting the ball. It travels 60 meters. Now there's some wind involved, right? and it's reducing the horizontal velocity. It's not helping the ball go faster, it's reducing its horizontal velocity. What do you expect to happen, right? So you want to think about that, because if you just get a number without actually thinking, is that expected? Does that sound reasonable? Then it doesn't quite work, right? So because the velocity is being reduced, the horizontal velocity is being reduced, the expectation is the ball should fall short of 60 meters, right? So we don't. The point is to go find out what number specifically, but it shouldn't be 60 meters, right? It should be some number smaller than that. So what we'll go do is to redraw our diagram. Doesn't hurt to draw more diagrams, especially when you have a couple parts. It gives you a clean diagram to start with. So let's have our ball right there. We still have that initial velocity at 45 degrees. Here's our x as before, here's our y as before, and we expect the ball to travel kind of like that, right? And there's a key point here about halfway through this process, right? So at the maximum height, it experiences some wind. So we're going to just focus on the fact that the wind is being affected, the ball is being affected by the wind only at a certain point, and that's right there, right? When the ball is at the highest point, maybe there's a short gust, that's what's affecting the ball. So we can break this process into two parts. We can say, how far did the ball travel for the first part of the journey, and how far did the ball travel for the second part of the journey? And if we add that together, that will get the total distance that the ball traveled, right? Because why do this? Well, up until this point when the wind affects the ball, it's going about its business as before, okay? But after the wind affects the ball, it's now going slightly slower, so we should think about that as a second part, right? So let's do this in two parts, where we're going to calculate XA, the distance that it traveled to get to the highest point, and then we'll get XB, the rest of the journey, right? Okay, so again, kinematic equations to start with, right? What do we want? We want an X position, right? XA, right? That's our final position based on an initial position, and we're adding the initial velocity in the X direction and multiply that by some time period it takes to get to the highest point. Now, this is not the total time, right? It should be half of the time, right? So it takes a certain amount of time to get to the top, and that's going to be half of the time it was in the air, right? So the time it's in the air, we already saw that earlier, right? So going back here, we have an equation here that relates the time of flight, right? So how long is the ball in the air based on how far it went? That's 60 meters initially. Based on the initial velocity, we can tell how long the ball was in the air, right? So we're going to use that again for part B. We're going to say the time, this is total time, not TA, but total time was equal to that range, that's 60 meters from the first part, but we'll just call it X here, because that's just the range, how far it goes, based on the initial velocity cosine of 45 degrees, right? So just to have a reference point, just to have an idea of what this looks like, let's put the numbers in. Oftentimes better to not put the numbers in, but just to see what's going on, let's just see if we can put that. So the total time, right? So 60 meters divided by 24.2487 meters per second, right? I'm trying to put in the number for v naught, the initial velocity that we found in the first part of the problem, times cosine of 45 degrees, right? So if we put this in, we'll get a number, we'll get 3.499 seconds. So that initial, no, there's no wind. How long did the ball travel through the air? Well, that would have been just about 3.5 seconds. Okay, so to get to the halfway point, right, the highest point, the ball is at the highest point at the halfway point mark in terms of time, what you have to do is just divide by 2, right? So when we say this is still t, but if we want ta, right, the time it takes to just make half the journey, well, that'll just be t divided by 2, right? So take t, divide by 2, and we can get ta, right? Which is going to be useful for our xa calculation, right? Again, the initial position in x, you can say 0. It's starting at the 0, 0 mark, right? It's starting at the center of the coordinate system. For the x component of the initial velocity, which we found earlier, we can put in v naught x is equal to v naught cosine of 45 degrees, right? So we got that over here, right? So up here, we solved for that already. We're borrowing some of that information for the second part. So let's now put everything together. We want to write x a is equal to 2.24.2487 meters per second, our initial velocity, cosine of 45 degrees times half the time, right? So it's not roughly 3.5 seconds, but half of that, right? So 3.499 seconds divided by 2, right? Again, we're dividing it by 2 because we know the time of flight, right? We know the total time the ball was in the air. So to get the halfway mark, we're just dividing by 2 to get the halfway mark, right? Okay, so putting that together, what we're going to get is 29.9977 meters. I'm carrying more decimal places just for accuracy, right? If you cut the decimal short, you'll get slightly different numbers. Okay, so we have the XA part. We need to go do the XB part, right? Okay, to do the XB part, what do we need? We need an equation that's similar to this. We need that the position is equal to a velocity times time, right? That's essentially what we're doing because there's no acceleration in the horizontal direction, right? So there's no a to worry about. So all you have to do is velocity times time. So we need a velocity in the x direction after the gust of the wind. So we'll need to figure out what that is, times TB. Okay, so times TB. And let's do the velocity first. So when you're trying to find velocity in the x direction after the gust of wind, well, before the gust of wind came along, the horizontal velocity was v naught cosine of 45 degrees, right? So that's what we had earlier, right? That's the horizontal velocity without any acceleration. It will always have that velocity, right? You need an acceleration to change that. If there's no acceleration, that doesn't change. So the wind momentarily comes along and reduces that number by 1.50 meters per second. Okay, so now it's a modified, slower horizontal velocity. Now let's put this into xb. xb is equal to the initial velocity was 24.2487 meters per second times cosine of 45 degrees minus 1.50 meters per second, right? That's our modified horizontal velocity. And then we have time, right? So what's the time? Again, we take the total time, 3.499 seconds, and divide it by 2, right? Putting that into your calculator, you should get 27.3734 meters, right? We're not done because we need to put the pieces back together, right? So what we're asked to find is how far, what's the distance that the ball traveled horizontally? Well, that's XA plus XB, right? So the X total is equal to XA plus XB. And so if you add the two numbers, you should get 57.37 meters, right? So as we said before, okay, you expect to have something shorter than 60 meters, right? So 60 meters is the distance that it traveled without any wind affecting the ball. But if the wind is slowing the ball down, well, it should go shorter, right? So it should go a shorter distance. And that's what we're finding here. We're finding that, yes, in fact, it did go a shorter distance by 3 meters or so. Okay, so as you can see, you can work this out, a little bit of algebra here. Just have to kind of work through the algebra. When you're going through algebra like this, it might seem intimidating, but the trick is to write things really, really carefully. Don't hesitate to just write more steps. If you try to do something in your head, right, you want to move and divide, and that you might forget to carry some term around. So if you're in doubt, just write it down step by step. If you're making very small changes to your equations step by step, then that's okay. You're very likely to not make a mistake, right, as you go through, because you don't want to drop a negative sign. You don't want to forget your A or tangents somewhere. So just write it very carefully, right? The trick with algebraic equations, whatever you do to one side, you have to do to the other, as long as you're doing operations on both sides. If you're going to multiply both sides of the equation by 2, fine, right? As long as you do it to both sides, it works out. So just very carefully go through the algebra and check me, right, if I did something incorrectly. Follow along and work this out for yourself. See if you agree with the method and the answers here. And you can see, you can do some pretty interesting problems here involving kinematics.